previous video told you about the principal components analysis and kind of got you started with it. Now let's actually use it on an audio recording. For this we'll need the standard few libraries that I tend to use. We'll need the Tidyverse, we need Tabber, we need audio, and we need Gene A. Reed. Okay, so with these libraries loaded, let's pull in some data. I've got some data in a convenient WAV file. And let's go transform this into a somewhat more useful format. If you're interested in what I'm doing, have a look at the video for Homework 3C, which explains how this works. In fact, it is the second of the two Homework 3C videos. And we're going to use the short time Fourier transform. And as in that particular video, I found a window size of a half a second works pretty well, but instead of a tenth of a second for the increment, do 5/500ths of a second. It's a little slower, but just fine. This takes a few moments to compute, and what we've gotten once we've computed it is a big pile of numbers in a nice grid that is a little bit inscrutable. So if you take a look at these values, you will see that there are many columns, many rows. It's a big grid. Each row is a time sample, or a time block, or time window, and each column is a frequency. It's many frequencies, so it's a very high-dimensional data set. Principal components analysis helps squash that down and fit it into a nice visual picture. PCA is a base R function and is ready to go. For you. Takes a few moments to run, but it's pretty fast. Okay, let's just make a quick scree plot to get a good handle on how many dimensions you need. And since there are many principal components, one for each column in the original data, let's just pick the first 10. So we'll use a filter for that. And you can see one big bar and a whole bunch of little ones. That means a two-dimensional PCA plot is probably pretty reasonable. Great, so let's take a look at it. So we can go ggplot this guy. So let's plot the first two principal components as suggested by the scree plot. I find it convenient to color this by time, but I have not put time into the original data, so I can't do that quite yet. So let's just take a look at what this is. So this is a two-dimensional visualization of this very high-dimensional data. Most of the variance is captured in this plot. Each one of these arms corresponds actually to a separate note being played. There's a bunch of arms that are overlaid on top of each other, which is a little hard to see. So as I said, it's helpful to color this by time. How do we do that? Well, we can add the time in there with the mutate, because we know what the time is in terms of the row number. And it's also given to us already. So now we can go ahead and color this by time. Now you can see that there are several distinct arms in this plot. So the principal components analysis kind of gives you a good idea what's going on. Notice how in particular, because notice how the color varies kind of smoothly out into one of these arms. What you're seeing is out here, out at the ends, are the actual notes when there's sound and nice and loud. This middle region here is silence. That's the sound of silence, or at least the visualization of silence. And what are the arms? Well, the arms are the note attack and release. Starting to play the note, it goes from silence, it ramps up. So it starts out silence, ramps up, sounding the note, and then ramps back down, back to silence. Ramps up, back down, and so on. Well, that's pretty neat. It's convenient, if you want to identify which note is which, to cut out the silent part. Okay, not so hard to do. All we need to do is we need to filter some kind of points so that we filter them that are far away from the origin. Now, the origin is not exactly in the middle here, but it's close enough. So let's build that filter. What do we do? Well, it's going to say something like Pythagorean theorem. So something like the square of PC1 plus the square of PC2. And if that value is too big, say, looking at it like 1,000, yeah, 1,000, that ought to cut the middle out. All right, and so now we've broken off just the tips of each of those arms. Pretty neat. Well, if you've got each of those little tips that you've broken off, you might want to cluster them to pick out the different notes. There are lots of different clustering methods out there. The simplest one is called k-means clustering. It's kind of dubious whether it always works. It doesn't always work, but it works well enough that we can use it. And if we don't like the results, we can just run it again, because there's an element of randomness. K-means is included in base R, so we don't have to load any libraries for it. It's going to take in all of the data we wanted. So it's going to take in all of this. We get rid of the ggplot. And just dump this into k-means. The slight problem here is that k-means it's not unsupervised learning, as in it doesn't completely work without our guidance. It needs a little bit of knowledge about how many clusters it ought to be searching for. I can kind of count roughly 5 clusters. Maybe you can count greater or fewer numbers. But if you would say, I want 5 clusters, it goes ahead and does it. Let's save the output. And what has it added? Well, the output of k-means is not tidyverse compatible at all. Let's take a look at it. It's, this crazy object here. But if you look at the cluster attribute, that is pretty useful. That's labeling each of the points in this diagram with a cluster number. Okay, so we want to merge that back into the data. Okay, so let's grab our tidyverse plotting command. Here we go. So we've got all of this. And what do we want to plot? Well, we want to take this and add to it. So let's mutate in a cluster number. And then we can go ahead, instead of clustering by time, we can cluster by, or color by cluster. And there you go. Actually, it did pretty good. You can see this is all one cluster, there's another cluster, there's another cluster, and these are several more clusters. There's a little bit of cluster contamination. You can see this is kind of the wrong color here, but that's sort of typical for k-means. Great. One thing you could do with this is you could actually say, let me go back and try to turn this into a piano roll kind of plot. That's actually super easy to do. We could just go ahead and do time versus cluster. And we've got something that sort of passes, roughly speaking, as an automated transcription of this piece of music. as in notes as a function of time. The problem is that these clusters don't necessarily correspond to notes in order, as in note 1 is not necessarily a lower frequency than note number 2. That requires some sorting. But this can give you an idea of the structure of the music just from the fact that we've got the data. This kind of PCA and then clustering process is pretty standard as a first pass for machine learning. Well, you could probably think of many other uses for this kind of processing, and so I hope this turns out to be useful to you at some point in the future. Hope you enjoyed it.